Now the final topic in state variables is controllability and observability. So we will start first with controllability. What is meant by controllability? You can first write down the definition. A system is said to be controllable, completely controllable, if every state variable can be transferred from any initial state x of t naught to any desired state x of t within a finite time by means of an unconstrained control vector u of t. We will take an example to understand this. You can draw a circuit diagram. Let us have a current source here, resistor, a capacitor, another resistor here, and here also you have a resistor and capacitor in parallel. Okay. Now let us say that this is the input I, the current source is the input. Now state variables will be the voltage across the capacitors. So we will take V1 and V2 here. These both comprise the state variables. Okay. Now you can see here this current source will give current only to this circuit. No current will flow through this capacitor, right? If you take C1 and C2, no current flows through the capacitor C2. So that means this voltage V2 is not affected by this signal, this source, right? So in that sense we say that V2 cannot be controlled by I. Let us say V2 had some initial value V2 of T naught. Now from this state to we want to take it, let us say this is equal to X. Now we want to change it to value Y. Can we do this using this current source I? We cannot do this. Okay. So that is what is given in the definition here. A system is said to be completely controllable if every state variable can be transferred from any initial state to any desired state within a finite time using an control vector. So now this state variable V2 is not being controlled by I. So we can say that this system, because V1 and V2 are its state variables, one of the state variable is not controllable. V1 is controllable but V2 is not controllable. So we say that the system is not completely controllable. It is controllable with respect to V1 but not with respect to V2. So that is why it cannot be completely controllable. Okay. So that is how you can understand controllability. Next, what is observability? Before discussing observability, you can write here, I cannot control or affect state variable V2. Okay, you write this as state variable V2. Therefore, V2 is not controllable. Okay. So now you can write the definition first you write for observability. A system is said to be completely observable if by the knowledge of system input and output over a finite time interval, all the state variables can be determined. Okay. In other words, every state variable should affect one or more outputs. Okay. So in order to understand this, we will take the same example. Okay. So the output we can take as V0. This is the output, and I anyways you can take as the input. Okay. So now V0, how you can write? It is equal to, if you apply the KVL in this loop. Okay. This resistance we can take as R. Okay. So the current flowing through this resistance is I. So now V0 will be equal to IR minus V2. Okay. So it is depending on current I, which is the input, and V2 state variable. Okay. Is it depending on V1? No, it is not depending on V1. Can you see any change in V1? If there is a change in V1, can you observe it at V0 at the output side? You cannot observe it. V2, if there is any change, can you observe at the output? Yes, if V2 changes by any amount, then it will reflect onto V0. The output we can see that there is a change in V2, but that is not the case with V1. So that is why we call V1 as not observable. The changes in V1 cannot be observed at the output. Okay. So that is why it is called not observable. So you can write here V0 is independent of state variable V1. So any change in V1 cannot be observed at the output. Therefore, V1 is not observable. Now, if you look back at the definition here, a system is said to be completely observable if by the knowledge of system input and output over a finite time interval, all the state variables can be determined. Okay. So that means if you know the input and output, that should be enough to determine the state variables. Okay. So in other words, every state variable should affect one or more outputs. So the output should have, in its expression, it should have each of the state variables. Then only it will be observable. Okay. Now we will see how to figure out whether a particular system is controllable or observable or not controllable or not observable. Okay. So test for controllability. So here we take a matrix QC we will take. This is equal to the B matrix, right? B matrix is a column matrix for a single input. So this column matrix will form the first column of QC matrix. Okay. Now the next row will be the AB matrix. Okay. So AB will be n into n matrix, B will be n into 1 matrix. So resultant you are going to get n into 1, which is also a column matrix. Okay. So remember, this is all for single inputs. Okay. So this will form the second column. AB will form the second column. Then third column will be formed by A square B, and so on till A to the power n minus 1 into B. So how many rows will be present here? N number of rows will be present. How many number of columns will be present? N number of columns. So QC is a n by n matrix. So this QC matrix, if its rank, right, row of QC means the rank of QC, is equal to the number of state variables, that is n in this case. Okay. Then we call the system as controllable. Okay. So then system will be controllable. This is the condition to test the controllability of a system. Another way of looking at this is, if the rank is equal to number of state variables, which is n, that means that the determinant will be non-zero. So that means another way of looking at this is, if QC is a singular matrix, that is determinant is equal to 0, then the system is not controllable. So you can just find out the determinant first. You first form QC and then you find the determinant. If it is equal to 0, it is not controllable. If it is not equal to 0, then it is controllable. If det of QC is not equal to 0, this means that it is a controllable system. So this is one criteria that is ever useful. Okay, we can always use it. Now another criteria is that if the matrices A and B, they are in the controllable canonical form. Okay, so you remember what is the controllable canonical form, right? If not, just go back and see the particular forms in which A and B are present, so that we call them as controllable canonical form. If that form we are able to represent, then the system will automatically be controllable. So that means, in other words, if a system is controllable, then it can be expressed in controllable canonical form, which is abbreviated as CCF. Okay, so the reverse will be true. If a system is given in a controllable canonical form, then it must be a controllable system. Next is test for observability. So similarly, here also we are going to have a composite matrix which we will represent as Q naught, QO. Okay, so what will this be? This is going to have its first row as matrix C. Okay, and the second row we will have as C into A. C is what? It is a 1 by n row matrix. What will be C into A? C will be 1 into n and A will be n into n. So you are going to get a 1 by n matrix, which is also a row matrix. So that will form the second row. Now the third row will be C A square, and so on till it is going to continue till C A to the power n minus 1. Okay, so that is how you form this matrix Q naught. Another way is, this is one way you can represent. Another way is C transpose will be the first column. C is a row matrix. If you transpose it, it will become a column matrix. Now that column will form the first column of Q naught. Then second column will be A transpose into C transpose, and so on till A transpose to the power n minus 1 into C transpose. This is how you form the Q naught matrix. Once you form this matrix, then the rest of the procedure is similar. If the determinant of Q naught is equal to 0, then it means it is not observable. If it is not equal to 0, then it is observable matrix. Okay, so this is how you find out. Another way of looking at is, just like the controllable canonical form, we also had the observable canonical form. So if a matrix is in the observable canonical form, then you can say that it is a observable system, because an observable system can be expressed in observable canonical form, that is OCF. So the reverse will also become true. If you have a system which is in the observable canonical form, then it must be an observable system.